OMS, the ordinary method of slides. And you realize the whole thing is based on one assumptions. It's assumed that, well, again, the principle, the basic principle of those like a method of slides are now you try to discrete your slope with like however many slides you want. For manual computations, you want to keep it less than 10. Otherwise, like there'll be too much for you to do it like manually. But in a computer package, they can do it like however many they want. Very likely the number of slides, they will do iterations. So they make sure the results from n versus n plus 1 slides like a smaller than, the results are smaller than our given tolerance, and they call it good. So the computer, they can keep like keep the iterations. 1 slide, 2 slide, 3 slide, 4 slide, 5 slides, maybe like I guess up to like a 10, 11, or up to like a 20 or 21 slides. You know, you should start to see there's not much difference when you like your slides is small enough. But anyways, manual calculations, I think it give you like a 6, 7, 8. That would be reasonable. So now you chop like your slope into different amount of slides, and now is a matter on how to determine all the internal force. So that's why like on a given slide, if you draw all the force on a given like body diagram, then you realize you need to solve for the internal force. So between slides, how would the force look like? And we're talking about different method. We're talking this class we only like select to try to finish within the time that we have, like because of time interest, we cannot like go through too many of them, but hopefully like I get you started to thinking about it. So when you move on to the next method, the first thing actually you look at, if you like, you know, try to study like between method method. So for example, if you use the GeoStudio, the slope W, you have all different kind of method. We talk about the Bishop and ordinary, so you have at least 2, and but the default one for the slope W is the Morgenstern price. But anyways, you have all this different type of method. The first thing you want to ask, like, what big difference between like a method to method? And very likely the main difference is the assumptions of their internal force. So for example, now for the OMS method, they assume the internal force, they are at the same directions that in parallel to the angle at the base of the slides. So that's why like this internal force xn over here is parallel with the slope at the bottom of the slides. And also they for conventions, they assume that between the slides, so on the same slide, on the left hand side and right hand side, the internal forces difference are small enough that they assume they are the same. So that means it requires you to chop down the force to be as small as possible, such that like, you know, so close to each other, and then like the internal force, they're about the same. Again, how small is this? How many slides you need? You know, you need to do you change from site to site. But at the end of the day, if you think like a computer, you will be through like iterations. When like n versus n plus 1 slides, the results are small enough, then they're quite good. So from this like a force diagram, and then like and also combined with the assumptions they have, they can solve for the normal stress. So throughout this like a free body diagram, other than the internal force that is like pretty much like an unknown, and also the normal force adding at the bottom of the slide is also an unknown. And they get around with it by pretty much canceling out the internal force and such that like from each slide, you have like a one equilibrium like conditions that allows you to solve for the one unknown, which is the normal stress. So here they can solve for the normal stress. And with this like normal stress being solved, and finally they can find out the factor of safety of your slope analysis. And this table here pretty much is the old school like computational program. The tabulate table helps you to eventually like solve for these equations. So in different slides, you will fill on each slide you will fill or you will calculate all the components, and at the end of the day you will add them up and do the divisions. That exactly the factor of safety you need at the end of the day. So that is the basic assumptions of OMS. And moving on, we also touch base on the Bishop method. So the Bishop method now is, again, when you try to think of different type of method, with a slide method, the first thing you think of is what are the assumptions on the internal force between slides. For this one, they assume the internal force, they are at horizontal directions. Is that true? Most likely not. But they do it that way is for especially this is not true when you have like a higher slope ground. If you have like a if you have a slope that we talk about more than 1-to-1, very likely incline or the force incline at 45 degree. But if you like assume it's just like horizontal, that's not correct. But like a Bishop, he purposely to do it for he doing it is for the simplifications of mathematical computational work. Because remember, they do this in the old days without a computer. But yet, like they set up the procedure and the methodology and make necessary assumptions. At the end of the day, like they got reasonable results that close to reality. But anyways, so they assume all the internal force being horizontal. Then from the free body diagram, they can start constructing, try to solve for the force. But realize that now you have one unknown, and also you in order to finish the whole analysis, you also bring in the another unknown factor of safety. But anyways, like we stopped here last time, so let's finish this one up. So now we have the free body diagram, and the next thing they would do is they just look at the vertical equilibrium. And taking positive as pointing up. So that's their reasons that like why they assume the vertical force, internal force, it just happen at absolute horizontal directions, such that like when they do the computations, those forces you can ignore, because now we're just looking at the vertical directions. You're not looking at the horizontal directions. So now you don't have horizontal force when you just look at the vertical directions. And pretty much like based on like the free body diagram right here, they sum of the vertical force. So the weight is always pointing down. The pore pressure, the vertical stress, which means the normal force at the bottom, and then plus. So pretty much this is the frictional force at the bottom of our slides. And you assume the factor of safety. So we get back to this factor of safety later. But now you assume a factor of safety. So the factor of safety come with the frictional force at the bottom of the slides. Maybe just try to be consistent. Just try to be consistent with my previous slides. So the vertical stress here means is the normal stress at the bottom of the slides. And this is what we try to solve for at the end of the day, right? The normal stress. So we got our equations. We got our equations right there. So we consider the vertical equilibriums, and also we consider the overall moment equilibrium. And then we take it positive clockwise, and we take moment at the center of the slip circle or slip surface. And then we do our math. The factor of safety equals to these are equations too. So we are considering two equilibrium here: the vertical directions and also the moment at the center. So we have two equations. Now you substitute equation 1 into equations 2. The factor of safety equals to oops. So the factor of safety is here, still there. So you realize there's two factors of safety over here. It's because like you have more unknown than enough equations to solve for the whole thing. So we talk about how to get around with that. So this is the equations that you got, and at the end of the day, you can simplify these equations into this formula, which is compatible with the procedure recommended by Bishop. So this is the equations at the end of the day, Bishop recommend in his kind of like a tablet form or like the old days like a software. So right there. Which this m sub alpha is equals to this value. So we have the cosine m sub alpha there is equals to this value. And the b is equals to the width of the slide, which is equals to L times cosine alpha. So now the trick is we try to calculate the factor of safety, but the factor of safety is in terms of the factor of safety that you assume. So this factor of safety here is the one that you assume. Same as here. So this factor of safety is the one that you assume. And at the end of the day, you calculate your factor of safety based on that. So you require some trial and error in order to find the correct solutions, because you realize you divide your slope into n different slides. So which means at least you have like you need to have like an n of like equations to solve for the n unknowns, because like each of them you have internal force that being unknown. Then, but you only have information for n minus 1 slide plus 1 factor of safety being unknowns. So which means you have more unknown than enough equations to solve for. So that's why at the end of the day, to get one of it, you need to assume a factor of safety first, and then you solve for the answer. And also this method is powerful because it can use for both total and effective stress. And this is an effective stress form. So what we have now, this is effective stress form. You can use for effective stress analysis. And for total stress, let me put here. So for total stress, what you would do is use C and phi. So not C pi and phi pi, it's just C and phi, plus delete the U terms, so you don't have the pore pressure. So this is for the total stress analysis. So I got questions for what range of assumptions for factor of safety? We'll talk about that when we get to the next slide. We'll talk about that. But before we get there, any questions up to this point? So what I mean here for the slide width is like, for example, like the slide that you have. So this is the slide that you have. So this is the width of the slides. And you have the angle alpha here, and also with the length at the base of the slide. So B is equals to delta L times cosine alpha. Before I move on, any questions from this Bishop method? To realize Bishop method is getting better because it fulfills two equilibriums: the vertical directions and also the moment. But it doesn't fulfill the equilibrium of the horizontal directions. It's a trade-off, because if you try to fulfill all of them, that would be too complicated in terms of doing manual calculations. So any questions? So for real design, I would highly recommend that you need to do. Depends on what how much time you have or what you're doing. If I work for the public work, for example, if I only responsible for 30% design, I will hire consultants to do the details 100% work, which means they are supposed to use flag or use GeoStudios to get the accurate final results. But at least like at my end, I will check their work. Or before I give out the contract, before I give out the project, I will check the work by using quickly. If I only have responsible for 10% design, I would at least do the single body method, which means I can solve for the whole thing in 30 minutes, at least get a proper answer, fail or not fail, what kind of factor of safety range the range I'm talk about. That may help you to get the range of assumptions for factor of safety. then like, this type of method require more computation work, as you can see. And very likely if you work for public work, you don't have the license of a GeoStudio, then you need to do all this kind of work. So if I'm responsible for 50%, or like, I need to get more accurate work, then I will go to computation work like this, which can cost me like, days to get it done. From like, setting up the drawings correctly, I need to work with the CAD technicians, make sure I get the CAD files correct, and make sure like, review all the boring logs, and make sure the groundwater table is correct, and review all the lab test results. I got the inner weight of the soils correct, and the friction angles, the string test, the triaxial test, make sure all the soil parameters correct before I start this analysis. So that's why soil strength is very important to visualizations. Nothing is correct at the beginning if your input parameters is wrong already. So you need to make sure all the soil parameters is ready. Think about, should there be drain or undrained conditions. Then now I can sit down and then like maybe set up my Excel spreadsheet to do all this like kind of work. It can cost me up to like 2 days of viewing hours to get this done. And then like, that part, like, which method should you go, highly also dictate on how much budget and how much time you have. But at the beginning of career, if you work for consultants, like, if you are the one responsible for 100% design, you can't just like sleep on it, like wait for anyone else software apart for you. You better do everything. Computer package, do a manual calculations of slide method, and also use a single body evaluations method. All of them. Just make sure you can sleep well in the evening. Because at the end of the day, you're going to stand on it, and you're building a career, taking out the money out of this. So make sure like you truly know what you're doing. Don't just blindly like rely on one source of results. Very likely like your computer package. Don't trust it. Just like the way that you don't trust me. Make sure you do it yourself. So any questions? Okay, so this is the kind of like the computation like a package. Like a tablet forms for you to finish the whole thing. So you would divide your slope into different slides, and you kind of tabulate each of the parameters of each slides, and you will realize actually like at the end of the day, the bottom part here pretty much is column 9, and like at your top part here, all these calculations is your column 16. So realize all of them is helping you to get there. And like I means like you need, I talk about this, you need to solve this by iterations, by assuming different factor of safety. So you will you have like at least like 3 trials: trial 1, trial 2, and trial 3. So those are trials with different assumed factor of safety right there. So if the first time you try, maybe you try factor of safety of 1, and then you try a factor of safety of like a 0.5, and then maybe try a factor of safety of 2. So you will get a better sense. Every site is different. I can't give you a firm answer. What is the one that what value you assume, or what kind of range you assume. But like if you do a single body analysis, which like can maybe give you a quick answer, what is the factor of safety, and then like maybe you got a factor of safety of 0.5, then now it would be reasonable to assume like 0.5, 0.5, and 2.5. So with 3 trials. So at the end of the day, whatever like you sum up here is pretty much just your bottom terms, and then like whatever like you sum up there is your top terms. Then you can calculate the factor of safety right there. You can calculate the factor of safety over there. And you do this by iterations, which means by here. So you have like assumed the factor of safety. So this is your trial 1, this is your trial 2, this is your trial 3. So you have your assumed factor of safety, and also you have your calculated factor of safety. And if you draw this like a 1-to-1 line, so this dashed line is a 1-to-1 line, which means it's like the slope here is 45 degrees. And this, at this point, means your assumed factor of safety is equals to your calculated factor of safety. So this will be your final factor of safety on that like an intersect point over there. So this is the intersections approach they use. You can do it by a simple graph on a piece of paper, or you can do it on Excel nowadays. So any questions over here? How to get this like a final factor of safety? Or overall this like a Bishop method? So here also give you like some like more informations. So if your slide have different type of soils, you need to average it. So what does it mean here? So you have like you have 2 different soils on your slides. Then you pretty much you calculate the weight and then represent like by the average numbers. 2-to-1 or 45. I think it's 45. It's a 45 degree. I believe it's a 45 degree over there. It's 1-to-1. It's 1-to-1. It's not 2-to-1. I believe it's 45 degree right there. Or like 2-to-1 means 45. Is that 2-to-1 mean 45 degree? I may be wrong. Maybe you may be right. But what does it mean? This slide here is whatever this number here need to be same as this number. So would that be 45 or 90 degree? I think it's 45, right? Am I correct? Or 90 degree? 45 degree, right? Yeah, 45 degree. Okay. Any more questions? So your homework 6. Oh yeah, sorry. So it is 1. This 1-to-1 here. It's not 2. It's 1. Yes, because I don't have much room. So this is 1-to-1. Any more questions? So your next homework pretty much is you need to solve for the also slide based on this method. And I have uploaded like homework examples on Canvas. So this is the homework assignment I give. I give like last time I taught this class. So so I also give you the solutions for this homework. So you have a slide like this, and then you are being asked to calculate the factor of safety based on both like an ordinary method of slides and also the modified Bishop method, and ask you to think about like the short terms and long term stability. So should there be drain or undrained conditions? So we have been talking about this like throughout the whole semester, and in design you need to think about it all the time. Should it be drained or should there be undrained? Should there be short term or should there be long term? So so short terms most case mean undrained, right? And long terms, in many cases, it means like a drained it. So if it is like a short terms undrained conditions, then you can use the total stress analysis. There's a C and a phi. But if it is like a long term in drain conditions, then you better use C pi and 3 pi. 3 pi. So in practice, you need to do the whole package from initial phase. Do it for clients, go get the soil samples and ship to the lab, and then like tell the lab which tests to be done. And at the end of the day, you, what parameters you get from the lab result. Should you get like C pi or C? Should that be you get a phi pi or phi? So you need to make all those decisions, and at the end of the day, because you understand what type of analysis you need, then you can use the proper parameters. So anyways, like both like OMS and Bishop method, they are method of slides. So you will, let me use other color. So the other nice thing of this one is they find the critical surface for you already. So you know the center already. I think at the end of this lecture, I will also touch base on, mention about like some procedure on how to locate the center. But anyways, this homework examples give you the center already. Then the next thing you would do, you need to change it into, chop this off into different slide. So this is number 1, number 2, 3, 4, 5, 6, 7. I think in the solutions, I do like 8 slides instead of 7, but you get you get the idea. So you chop it into different number of slides. And how much you need, you make the call. And like the more that you make, the thinner the slide gets, the more accurate you will. But you understand that at some point you will get saturated, which means like n versus n plus 1 slides, there's not much difference. For example, like 10 slides versus 11 slides, the difference will be very, very small. So, but anyways, like a 6, 7 slide or 8 slide, should be sufficient. So you have all this like a different slides. So on each slide, you can have the parameter you need. So a question for you guys, for examples. So question for you guys. So for when I look at this slides, when I look at this slide, if I'm looking for phi pi, what kind of friction angle should I use? So for anyone, have you? So if I need to use phi pi, and maybe also the just when we talk about the phi pi, what kind of like a friction angle is used? So those are like a sand. So the phi, assume the phi and the are the same. I want you to think about it. So for this slide number 4, what kind of phi pi you need to use? And also, what kind of unit weights you will use? Or we just talk about the phi pi first. Anyone? You can either speak up or type your answer. Anyone? $31, $35. Anyone else? So when you answer my questions, you can answer to public. So someone say 31, someone say 35, and someone say 30, 31. So Tommy, why 31? I should have picked on anyone. but I think Tommy got it right. It should be 31, right? Because I remember when we calculate the strength of the soils, right? When we calculate the strength of the soil, oops, he's correct. It should be 31. And when we calculate, you think of at the beginning, when we try to hypothesize the whole thing, the T here, right? The T we try to talk about over here in terms of the friction angles, we are talking about the frictional force at the bottom of the slides, at the bottom of the slides. So that's why when you have a slide like this, you have a friction angle at 39 degree here, and you have like a another friction angle of 31 degree here. Because this slide you have two different type of soils, but you just look, for string wise, you should just look at the bottom. That's where you're at. That's where the the resistance force come from. And when you look at the unit weight, then you need to use the average. So I think the Bishop method will ask you to calculate the unit weight times the height. So you would take the center. You would take the center of the slide, and then you have H1, H2 right there. So any questions? And one more time, if you want to calculate the pore water pressure, So this is the groundwater table here, right? So for example, for slide number 2, you will calculate the pore water pressure at this point. So you have this, I don't want to use H, so maybe call it the Z of water. So the pore water right there will be equals to the unit weight of water times the depth right there. Now you can always measure the scale in the field. So if you use on a piece of paper, if this is like a 2 inches, then 2 inches applying this scale here. So 2 inches means 20 feet. That means you have 20 feet of waterhead right there. So any questions? So I'll also give you the solutions of the example homework, so you can calculate. Pretty much, this is the same table you have on your lecture notes or your handouts. So this time I have like an X number of slides, and for each slides, I walk through all the columns, and at the end of the day, I can calculate the final factor of safety with this program right there. So any questions? This is OMS. OMS is supposed to be simpler than the modified Bishop. So I redo the whole analysis with the Bishop method. So I assumed factor of safety right there. Well, I think I didn't put it down. Well, you can see it there. So I assume the factor of safety as 1, and also a 3, and also maybe like a 0.25 right there, a 0.5, or maybe 0.4. So 0.4, 1, and 3. So I do it like a 3 times, and I got like a 3 different like a factor of safety. And at the end of the day, I plot out the same graph, and then like the intersect point. This is my final factor of safety right there, slightly less than 1.5. So I expect you will do a similar like exercise for your next homework, but on the also site. So one more times, your homework, and you can find all the information from this like a stock paper. I encourage you each read the whole paper. Read the whole paper. So it's a classic case history, and you do have a groundwater table. I think table 2. So this table 2 right there, give you all the friction angle you need, and also you have the unit weight. You have the unit weight, and also you have the friction angle. So if you given a range, then you better like you better make the assumptions. So if you have 2 choice right there, you make the call, and your homework you tell me why you assume this number. You can pick like the average over there or the average over there, but you need to convince me why you pick that values. Because at the end of the day, or if you want to go to the next level, you even can do a sensitivity analysis, which means like you take the lower bound and upper bound and do the analysis 2 times and see what kind of results you get, and then you get a range of factor of safety. I let you to do it. Or if you read after reading the paper, they give you some insights that you should use residual values, or should you use the fully softened like a values. You make a call. You make the call, but you explain to me why you use that number. So you have all the friction angles already and the unit weight. Then you can find out all the dimensions on this plot, because the scale is given to you, so you have all the scale. And also you know the water table is too. You know the water table is too. So I let you to do the calculations. So the other trick you may need to find out the moment arm. I think that may be like a little bit challenging, but I let you try to figure out how to do it. You have the slip surface, and you should know about the moment arm. So any questions about this homework before I move on? Question 1, question 2, and question 3. So anyone started the homework yet? Or it was something like you don't want to think about it before the weekend? Anyways, so next, moving on to our lecture. So pretty much we finished the 2 methods, both the sunny tonight. So the both method is the slide method, and there are more. Actually, there are more. If I draw my head, let's talk about this first. Since it's good that like everything's still like a fresh mind. So we talk about the OMS and also the Bishop method. So what kind of assumptions on the OMS or the Bishop first? Because we just finished this one. We assume we have horizontal. We assume we have horizontal slide force. And you satisfies the vertical equilibrium for each slide. Not only vertical, you also satisfies the overall moment. And for the OMS that we talk about, the major assumption is the psi force parallel with the base orientations. And this method here I mean at the side, not the slide or slides. So I mean this is the psi force. So within each slide, this is the psi force. And for the method of OMS, it only fulfill the conditions of the moments. It only satisfies the overall moment. So for each slope, for all the slope that we deal with, statics tell us you have three equilibriums: the horizontal equilibriums, the vertical equilibriums, and also the moment, because it's like a rotational failure. Also the moment failure, the moment equilibrium. So the OMS methods is only work for overall moments. So this method is good, it's perfect when only phi equals 0. And it becomes also this method becomes too conservative. As phi becomes important. And this method becomes very conservative when both phi and pore pressure are important. For the Bishop method, is overall good, except cohesions is important. And the deep rotation failure is not and it's all. And also realize for these two methods at the beginning, you only work for circle. And it's a method of sides. You only work for circles. You only work for circular slip surface. Oh, guys, I think my camera is dead. So my battery is gone. Give me 1 second. I forgot to charge my camera. Hopefully, back up. We're back up. But anyways, any questions? So this bring up to the to the next level is that when you have a slope, that is no longer just circular failure. What happens when you have a wedge? When you have a wedge failure, which means you have a slope like this. You have a slope like this. When the case that now is no longer, you can identify that no longer it is not like a circular slip. It could be the case that you have backwalk material there. So and you know that when you fell, pretty much your soil will slide on the rock, or like you have a weak plane right there. You know that when you fell, you will fall as a wedge instead of like a circle. So that's something else like we need to deal with. So the next thing I want to talk about is the wedge method. So the wedge method is try to solve the problem with force equilibrium. Let me try to bring up my camera. Oh, come on. Okay. Let me try to have my camera back on. Okay. Okay. I'm back. Anyways, so this gives you the this method using force equilibrium. They try to fulfill both vertical and horizontal directions. It works for the long circular. And infinite slope. So at the beginning of this lecture, we introduced like when you have infinite slope, but that only works for sandy material, and also only work for total stress analysis. We didn't take account of the water table, but this one gives you the capability to do it. But it's quite complicated. Not complicated, but like just like mathematical intense. There's a lot of like equations you need to handle when you have a slope that try to fulfill the equilibriums at two conditions. So it involves like a two-step. First, you assume the factor of safety first. And then you will, the way it works, you will like chop, or you will divide your failure wedge into different sections. So in this case, for example, we divide it into 3 different sections, 1, 2, and 3 right there. And then you will begin with the first block and try to balance all the vector force by iterating the factor of safety. So for example here, well, first of all, you start with like a block number 1. So this is my block number 1. So this is my block number 2, and this is my block number 3. So you start with block number 1. The most simple thing is, first of all, if we try to list out all the force right there, first, the most simple one is you have the weight. The weight is plummeting down. And you know that it has like a friction force against the bottom of the slides. And you will have a normal force adding up against the slides, the slip surface. And in between slides, there will be a resultant force. So this is block number 1 adding to block number 2. And then you know that there will be a resulting force adding if it's formed like a block number 2 is at block number 2 form block number 1. So pretty much you have this force and this force here. So block 1, 2, sorry, force 1, 2, and then force 2, 1. So go back to block number 1. We can solve for T1. So W1 is very obvious. So the weight is always the most obvious one. And T1, you can solve for it with the Moore column. This equals to N1, which is the normal stress, times the friction angle, plus the cohesions, times the length. So this is the length. And then divided by, so this length 1, and then divided by the factor of safety. So you need to assume the factor of safety to start with. So you assume one factor of safety first, and then like I see what you have. So that's why it can be tedious. You know, I don't, you never know what factor of safety you should start with. You will be kind of like few iterations. So if you assume one values and at the end of the day you realize you're far off, then you will go back to try another one, and then a couple of times, and then you will get a sense on what type of factor of safety you should use. So this is quite tedious on this type of analysis. But anyways, you know like the T1, and if phi pi equals 0, then your T1 will be equals to CL1 over factor of safety. So that will make our life a little bit easier if this is a cohesive material. There's no friction angle. So you know your W1. And now you know the orientations of T1. So this is your T1, and you can calculate this. So this is the orientation of T1 is a vector. So you need to know the orientations and also the scale. So let's say you know T1 now. So this is your T1. This is the directions of T1. And the next is you also know. So let's try to keep it consistent with the color, make your life easier. But I just want, well, nothing wrong. I just want to make like a more, which is better to see it. So this is T1, and let's say this is the N1, right? So N1, this is a 90 degree. So you know the directions of T1. And then, like for example, you can calculate the magnitudes of T1. So now you know like a T1 is this much, for examples. So T1 equals to the cohesions times safety. So you know it's right there. And then now you also know the orientations of N1. you start from there. Well, I just move it here. You will make my life easier. So this, the the directions or the orientations of N1. So this is where the N1 pointing to. You not necessarily know N1 because you don't know N1. But there's a diagram method helps you to solve the problem without knowing T1. Sorry, without knowing N1. You know T1. So I move the scale, just make my life a little bit easier. Oops, like this. So now assume this much here is what you calculate. So T1 is easy. You can calculate that, but you need to assume factor of safety. But N1 you don't know, but you don't need to know because you know W1, you know T1. And in order for this to be within in equilibriums, at the end of the day, you must be a closed loop. You must go back to where you start. So this is your F12, right? So F12, we assume that it is the horizontal directions. It's a horizontal internal force because that's the way that we draw our wedge or block. So this one must be closing here. So with this, it helps you to calculate the amount of N2. So here is the amount of N, right? And then with this method, you can also calculate F12. You can find out F12. You can find out F12. So any questions here? I don't want to lose anyone. But everything you realize is not based on the assumed factor of safety you start with. If you assume it as a different factor of safety, the scale at the T right there will change. And then you will couple the N values and also the F12. Is it a correct factor of safety? We don't know until at the end of the block. Because if the factor of safety is correct, at the end of the day, all the force will be caused at wedge number 3. So any questions here? I don't want to lose anyone. Any questions here? Okay, very good. So moving on the second wedge. So you find out F12. So you will know you find out F12. So you will find out F212. They are equal magnitude, but just at opposite directions. So at the beginnings, what you know is the W2, right? So this one is kind of so W2 is kind of like a free informations. As long as you know the area, you know the unit rate, you can find out the rate of the block. And now you will know F21. So you know the magnitude and you know the directions. So you can construct F21. So this is F21. And the next thing you can do is again the T22, because the so T2 is in this directions, because T2 is pretty much as long as you know the cohesions and you know the length of the bottom of the slides, then you can find out. Of course, you have a consistent factor of safety, and then now you know the orientations of your T2, and then you bring it to your force diagram. You also know the amplitudes. Then you know the orientations of the normal force and here. So you know there's orientations, and then you will have this this will make my life easier. So let me stop there. So if you realize it has a very hard time to close the loop, then you will know the factor of safety you assume at the beginning is incorrect already. But anyways, let's say like you go there, you know the orientations. So again, like I just make my life easier. So that's the amplitudes of the T2 is supposed to be. And again, you only know about the orientations of N2, but you don't know about the magnitude of N, the normal force. But that's okay. This will help us to find out now, because at the end of the day, we also assume that our internal force at the second from the 3 is at this orientations. So we can find out the magnitudes of that. And it is given at to the third block, but at opposite orientations. So with that, we can solve for it here. So finally, you will get to all your final block. So you know the weight of this. And then now we know the orientations of this, adding at the other side. You also know the P3 of it. Well, first of all, like you have the weight, you have your friction angle, and then you have your M3. So now you have your friction angles. I'm sorry, the frictional force. You know you will go this way, which you can calculate. Be right there. And then you know that at the end of the day, it should be close from the, so to make my life easier, I'll do it again. So all the scale need to be correct. Otherwise, like you won't close. So this is W3. So this T need to be a little bit longer. I mean, this like internal force. So everything need to be at the scale in proportions. So you know, if your weight is this much, your F need to represent the scale as the weight. So this is F32. Let me use consistent color. So red is the frictional force. Oops. And this need to be in this directions. And at the end of the day, you also know you don't know your normal force right there, but you know the directions, you know the orientations, and this need to be close. So now I'm not closing. That means I'm not correct. So should be like something like this. So maybe the F, if I do it right, you need to be like even like at a higher. So if I at this point, you see like this is a perfect examples. If I'm at this point, and if like my force at the end of the day, like you know, I realize at the right orientations, but my end is not closing. Go back to my original point, which means the factor of safety that I assume at the beginning is not correct. And I need to redo the whole thing from the beginning to assume another factor of safety. At the end of the day, if I do it correct, I should be able to close my loop. So this is a paper killer. If you do this like a truly by manually, you need to use paper after papers, trial after trials, and then you can get the factor of safety correct. Okay, so we have been talking about the slope stability method. We have been talking about slope stability method. And don't forget, like at the beginning, we mentioned about this. There's different types of approach. Well, the two main kinds, the single free body types and also the procedure of slides. And we spent a fair amount of time on the procedure of slides because that's more accurate, but require more computations work. And the procedure of slides can be quite accurate, or to a degree that people feel comfortable with. But it depends on how many slides you have and which method you use. At our end, for this class, the expectations is the theory behind, and also when it comes to have different options, different method for the procedure of slides, and each one how it differentiate from each other. So that's the expectations for you to know as engineers. So the procedure of slides, particularly we look at the two types, the OMS, the ordinary method of slides, and also the simplified Bishop. So those two methods you'll be required to solve it for homework 6 manually. So with those two methods, we talk about this, and the key difference how to assume the internal forces. So OMS, what the major assumptions is the side force is parallel with the base orientations. So you have a slope, and the slope end up at the base you come with an angle, and we assume the side force is parallel with the orientations of the base. A Bishop method will be a slightly different. They assume the force is horizontal. So with those different internal force assumptions, and also purposingly doing it, it helps you to solve the equations on the free body diagram of each slides. And then it helps you to tell whether it satisfies what kind of equilibrium conditions. There should be three different type of equilibrium conditions: the overall moments, and also the verticals, and also horizontal. The OMS method only satisfies the overall moments, versus the Bishop method try to come up with a more accurate, more realistic type of analysis. And then now the Bishop method is satisfied 2 out of 3 conditions. It satisfies both vertical and also the overall, but it doesn't satisfy the horizontal. So the trade-off of the Bishop method is you need more computational work. So homework 6, when you do your assess the slope stability for the K history, and also you will be using 2 different methods, and you will see the increased amount of computational work you need when you move on from Bishop to OMS method. And accuracy, so for us to as engineers, we need to know which method is better, and which method give you what kind of conditions. So the Bishop method seems more computational work is needed. So you can expect it will be a little bit more it will be more accurate. It will be more accurate for the Bishop method. So those two methods is the method that like only satisfies the circular subsurface, and why not, like, let's finish this table while we are here. So for the circular method, so we are still talking about the circular method. There's two options. There's two more options, which is the Jambu method and also the Spencer method. Those method also those method also satisfies the circular slip surface, and those are a little bit more like more advanced method, and the computation work start to be even more like a longer, that like this cause, I mean, like, for classroom instructions, is start to be very hard to finish the whole thing. So that's why I didn't like go through those two methods, because if we try to list out all the equations, could be like, page after page. But like when we compare starting from the Jambu's method, compare with the Bishop and OMS method, this method satisfies all three equilibriums conditions. So this is the nice thing about it. So what being different here now is the side force. They really solve for the side force, which means like the orientations of the side force is not like kind of restrained on parallel with the sides or like being absolutely horizontal. It is the resultant force. So each side force have a different like orientation angles based on like the static analysis, each of them. Oh, I don't know, I've been struggling with the pen for the whole day. So how they do it is each slide or each like calculations, they go through iterations. So you realize all this like a slide procedure is you try to solve for something that you don't have enough information or equations. The number of unknowns is always more than the number of equations that you have. So that's why when you do your Bishop method, you need to do a trial and error for the factor of safety. And at the end of the day, you can solve for the overall factor of safety, starting with the assumed factor of safety. So like here, the Jambu's method, you don't know about the side force, but what you can do is you try to move up and down on the truss line. So you try and error on the like internal force until you find a line that gives you the lowest amount of energy, which means give you the lowest factor of safety overall. So what does it mean here? This method. So you have your slope. You have different like a slide. And then there's like what they call the truss line. So this is the truss line. To give you all the resultant force. So they will use like a trial and error method to move this truss line up and down.
until you find like a truss line that gives you lowest energy. So that's a lot of computational work, a lot of trial and error. So pretty much like, in the old days, they need to do it by hand. You take them like a days or weeks to try to like do everything on the paper. But like with a computer program, nowadays you can get it done in seconds, just like iterations and trial and errors. So that's why like, as an engineers, you are not like, trying to be the one that try to solve for everything on paper or like, plug in the equations type of like a computational work. But what you're doing is what like, what we require, like the modern geotech engineering, yes, is understanding all this background, and then you can come up with an approach that is the best for your project. So this like a Jambus method is kind of like a trial and error, and at the end of the day, a lot of computation work, but it's very good, but it is very difficult to program. So that's why like, a computer package like a GeoStudios, SlopeW, UTexas, or GStables, they charge a lot of money. They charge a lot of money because they program that. They find ways to program it. The other like two method, OMS and like the OMS and BitShop method, I believe like a graduate students. A graduate student should able to program them, OMS and BitShop method, either on Excel or MATLAB. I don't think it's too hard to program it. But starting on the Jambus method here is very hard. It's very hard to program. So the next method is the Spencer method. Again, it satisfies all three requirements. So those methods are the better ones. It satisfies all the requirements. And you assume all the side force. Parallel with each other. Which means like well, like when I draw this, like it seems parallel, but like for the Jambus method, it's not necessarily parallel. But like for the Spencer method, they are parallel. Because like for the so pretty much this is like the Spencer method. But like for the other one, it can be something like this. So you keep search a line that, so this is kind of like the Spencer. Method. So at the end of the day, like each like force right there, they're parallel with each other. But like the Jambus method we talk about, you will keep like searching the lowest energy truss line until, so this is the truss line that like you keep move up and down until you find the line that, or you keep like searching a truss line that give you the lowest amount of energy. So this method, you assume all the like a side force, they parallel with each other, but this is not physically correct. It's simpler, but this than the Jumper's method, but it's not absolutely correct. So the accuracy of this one, at least this is better than the OMS and the Bishop method. But you need to realize that they are better. This method are better, but there's a trade-off, which is much more like requirements in computational work, which means at the end of the day, in order to do the Spencer and the Jambus method, you don't have like at least you don't have, it's very hard to like doable even though with a table, especially like those like is still manageable for OMS and Bishop, but for Jambus and like for Bishop method, pretty much you need a computer program. You will need a computer program. You will need a computer program. So those methods are the common one, and like your computer program, Slope W, they also have the Morgenstern PIES method, which is their default method. You can look up the internet or look up the any textbook or the manual, like then you will find what kind of assumptions that they have over there. So going through a semester of coursework, we go through all this, just pretty much just try to help you to get started, able to to know how to think critically, or like making all those engineering sense on, or what kind of informations you should be aware of when you come to slope stability. So those like method are like for circular, and for the Jambus, and also for the Spencer method, you can move on to the case that where you don't have a circular slip surface. Maybe you have a wedge a failure type of like geometry. So like a case like this, for like a scenario like this, when you don't have a circular slip surface, now you have a failure surface like this one. So you fail as a wedge. Then there's a wedge method that you can apply. So wedge method pretty much is just like try to solve for all the force equilibriums. So you cut down like your slide into different pieces of triangles or trapezoids or rectangles, and you solve for all the forces. At the end of the day, you can find out the factor of safety. And the way we do it is like first, if we try to finish this table first. So the assumptions are, well, first of all, this so-called is the wedge method. And the assumptions for this method, like we start last time, all the side force resultants are horizontal. And for the equilibrium conditions, you only like satisfies the vertical and horizontal. It didn't fulfill the moment equilibriums, only vertical and horizontal. And the accuracy of this method, the factor of safety, usually is low by 10 to 30%. It's not so accurate because like first you assume all the force, all the side force is being horizontal, which is not true in the case, and also you didn't take account the moment equilibriums. There's like another like method, so that's like a wedge method, and Taylor also come up with another approach. They try to assume, whoops. Sorry, my pen is not working well today. I don't know why. So they try to assume the side force resultance. Is average. Of tops and base. And you only like satisfy the verticals and horizontal directions only. And also the factor of safety is about 10% too high. So you can tell the side force, the assumptions of side force is very critical. You know, if you change assumptions, you can change your results by almost like a 30 or 40%. And you just need to be aware of which method you're using and based on what constraint that you have. You know, you could be working for a firm or you're starting your own business at the beginning. You can't afford like buying like a Geo Studios. Then based on what you have, you need to come up with an analysis. Then you need to like, you know, all the advantage of disadvantage of each method. Even though like, you know, you work for a top-notch firm, and then they can buy whatever like they can subscribe to whatever computer package they have. At the end of the day, as engineers, you know, you don't want to trust the computer program at all, because at the end of the day, like who knows, like you mess up like one input or like one like you don't have like, you know, a very like a clear view on like what kind of parameters that you input, but like going through the hand calculations quickly, or you know, or like, you know, be reasonable amount of time, you work on the numbers, you work on the equations, then at least like, you know, give you a sense on which parameters being like sensitive, and you know how would affect your results if you change your assumptions. So this table only like allow me to put like a 6 method, but as you can tell, like computer package like this one give you much more, and this and even though like all the options over there, it's not all of it. There's many different like approach or different like a method being available. As a geotech engineers, the requirement is before you use any of those methods, you need to understand everything before you like, you know, click the next buttons. For example, if I'm using the Spencer method, if I don't know the assumptions of Spencer method, I better not using it. So like, you know, it's not just about like finishing the computer program, it's knowing all the like stones behind it. You need to turn all the stones. You need to know all the like assumptions and procedure. So if I want to use the Bishop method, you know, what I will do is I need to go back to the manuals or the original like papers, and try to like understand the whole thing. Or even though I will do hand calculations myself quickly, if I can afford the times, I will do a method of slides. If I don't have the time, maybe I will do a free body, like a single body diagram method, single body like analysis method to get a quick sense on what's going on the site before I truly like blindly believe what the computer telling me. So any questions? So remember, like on the slide method, we did on like a course, finished everything on last week. But the simple concept is now you have your slide, you cut it into different blocks, and then you start from block number 1. You solve for the internal force by knowing the weight. The weight is the very first one that like a very simple, very obvious, and then the next is if you know about the solid properties, then you can find the frictional force at the bottom, which is a T right here. So you know the weight, and also the frictional force at the bottoms. Then you also know the orientation. You not necessarily know the result on the magnitude of the normal stress, which is the N right there. Is the normal stress N is always very hard to find. But now this like a method allows you move on without knowing the magnitude of the N, but you need to know the orientations of it. So this is going down. The magnitudes and the orientations of the frictional force, but now we just need to know the orientations of the normal force. And in order for this method to work, the resultant force must close the loop. So end up like you will indirectly find out the magnitudes of the normal force and also the resulting force, and everything based on the factor of safety that you assume. So you keep on this procedure, you move on to the next block, and then you go to the last block number 3. And if you pick up the factor of safety correctly at the beginning, at the end of the day, you should have close. So at the end of the day, this diagram will give you a closed loop if. So that's a big if right there. If your factor of safety is chosen correctly at the beginning. Sorry, my pen is not working very well today. I don't know why. So this factor of safety means here. So pretty much this is a trial and error method. You pick a factor of safety, it doesn't work. You choose another one. If this is too large this time, like you need to bump up your factor of safety. And next time it's too small, then like the middle ground to go to. You keep try and error until your last block, you got a closed loop. You try a couple of times, then you get a sense. If you just off by a little bit, then next time, what's the final adjustments you need to make. So this pretty much is the wedge method. Any questions? And those wedge method, the Taylor method or this one, highly depends on what kind of horizontal force. So those horizontal force right here that you assume in between like blocks. So this method assumes they're horizontal. Taylor's method, they assume you would take the average from the top and bottoms. So the orientations from the top and orientations from the bottoms, you take the average of it. Any questions? You guys want to work on a problem like this in your final exams, maybe? So be expect the final exams, that will be like, since like this topic hasn't been covered since the midterm, so you expect like at least 1 or 2 questions from these topics. And the critical state soil mechanics is also always important, so you'll come back to you again. Or maybe I'll talk also like a test a little bit on consolidations too. Okay, if there's no questions, then like we move on to the very last slide here. So we talk about the the slip surface, the center of the slip circles. So how to find the center of the slip circles? So there's like a hump and like a ramp, up ramp, and a Dwight 9072. It provide a procedure to search for the center of the slip circles, and you just buy like a coordinate setup. So if this is your slide, right? So if this is your slide, this is your slope, and assume like you try to search for like this slip circle with like diameters or radius like this. Oops. So you define the circles. First of all, the circle, maybe more clean. The circles. So this is the toe of the slip circles. So you come with a coordinate pairs of x0 and y0. So from the vertical, you assume the location of the center is a vertical distance of y0 above the toe, and also a distance x0 away from the toe. So we set up the x0 and y0 like our conditions. And then you know the height of your slope. Then you can find out this x and y coordinates, So this is the h0 and y0, x0 and y0 like divided by the height of the slope, divided by the height of the slope. So pretty much you're solving for the x0 and y0 there. So you give a ratio. You give a ratios on this x-axis and y-axis, and depends on your friction angles of the soils you're dealing with. So if you have a friction angle of 30 degrees or 40 degrees in general, then you pick the friction angles. If you have different like layers with different friction angles, and you will maybe average the friction angle for the whole site to get you start. Remember, this is just a setup. This is just kind of like rough estimations to get you start. Because if you have a slope, the first thing you need to do is to estimate the slip surface and the locations of the slip circles. You need to have somewhere to start. A computer program is doing exactly like this. They try to like compile like many different trials until they find a critical slip surface that gives you the lowest factor of safety. So pretty much they will do is like they have one point to get started, but they need some guidelines, or they need some hints to get started. And this is like to help them like the computer to get started. Or in the old days, like you don't have a computer, you need to do like do some try and errors again. So you will like try a couple different points along this grid right here. and then like you keep narrow down until you find a spot that give you like a zone that give you like a like a family of credit factor safety, like that being lowest, and then from there you will conclude where is your critical slip surface. So to use like this like a diagram here is, first of all, based on the soil friction angle that you have. So here, this dashed lines are the friction angle. So you have a friction angles of like a 0 degree, 1, 2 degrees, and up to 30 degree and 50 degree. Those are the dashed line. And the second thing will be the geometry of your slope. The geometry of slope. So this like a beta right there pretty much is the orientations of your slope. So you are dealing with this angle beta, which is this the sloping angle of your slide. So pretty much like you can calculate this one, the tangent beta, whoops, is equals to A over B, and then the cotangent beta, which is the flip of it. So this cotangent beta right there, which is the ratio of these two dimensions of the geometry, then you will give you the soil line. So you have a 1-to-1 slope, 2-to-1 slope, 3-to-1 slope, and 4-to-1 slope. So you only can handle pretty much up to 1-to-1 slope, which is 45 degree. So this method is those like give you those like grid to start from. So again, like actually like the dashed line is more than the friction angle. It gives you those parameters, lambda. So lambda C phi. So this is lambda C phi is calculations of this formula. So I take it back. Sorry. So the dashed line is not just the friction angle; it's also the cohesions. So you need to calculate this like a dashed line with this formula. So this is the procedure that they recommend. So this line here will be equal C equal C equal 0, and this line here is representing free angles equals 0. So you have a sand type of material here, and then also you have the clay type of material right there. And whatever you calculate on the parameter lambda right there will give you a number. So you know the sloping angles, and also you know the this like a parameters right there will give you like a coordinates. So from the coordinates, you can find out the locations of X and Y, and then you can approximate the locations of the slipping circle sand. So any questions here? So this is very rough. These are very rough estimations, but like hopefully to get one engineer start on their first trial on the factor of safety. So after like the first locations, what a computer will do is like they keep trying at different like points, and then until like they find the lowest factor of safety. And like if you're doing like manual calculations, you need to try a couple of times. You need to try a couple of times with different locations, And like for exam purpose, for homework problems, time constraint, like limitations right there, I will provide you the slip surface. I will provide you the center of the the slip circles, such that you don't need to go through this progress. But like, you know, at least I want you to give you have a sense on how to get started. Any questions? Before I wrap up, there's like a slope stability topic. Any questions on this topic? So pretty much we finished